Now the technical difficulties are done. Welcome to the first Compass lecture of the semester. We're excited to bring back the Compass lecture after a one semester hiatus. We will be holding lectures most Fridays this semester. There are going to be a few Fridays that we aren't holding lectures, but we have 8 speakers lined up for this semester. So there's going to be a lot of great talks. Hopefully you enjoy, tell your friends about it. Second thing, if I know many of you have already signed in. If you have not signed in already, we have a sign-in sheet. I will pass this around. If you already signed it, just pass it along. It really helps us keep the Compass lectures going and show the department that this is something that is worth doing. Next, we also have tea and snacks in the back. Feel free to take some now, and then after the talk, feel free to take some more. And if Madeline wants to stay for a few minutes to talk, if you have questions for her, then that'd be great. And yeah, we'll get started. So our first speaker of the semester is Madeline. Madeline grew up in Chicago, where she was first exposed to physics. I should be by the mic. Madeline grew up near Chicago, where she was first exposed to physics through outreach programs run by Fermilab. She spent her undergraduate years at Harvard, where she dove into the world of particle physics, working on the ATLAS and the DUNE collaborations. She came to Berkeley in 2019 and switched to the subfield of atomic physics, joining Holger Mueller's lab and working on the alpha experiment. So harkening back to her particle physics roots, she's most excited about using atoms to probe the standard model and search for new physics. And besides science, she loves music, books, coffee, and spending time outside. Yeah. Let's welcome our first speaker, Madeline.
Great, yeah, so I'm going to tell you guys today about my experiment here at Berkeley, where we are testing the standard model with atom interferometry. So I'm just going to get into it. Nice. Okay, so a little bit about me. I know the Compass talks like to have a little bit of this sort of personal story. So I grew up in the Chicago area in a suburb called The Grange, and as Danya just said, I was first introduced to physics through outreach programs run at Fermilab. In particular, they had high school lecture series and also a high school intern program that I did where I was doing dark matter searches with bubble chambers as a high schooler. That was a really cool experience. It got me really excited about physics. I went and did my undergrad at Harvard, where I was a physics major. I did particle physics type research while I was there. I found it really fun. And then I came to Berkeley in 2019. And so for the past 5 years now, I've been working on this experiment. You can see in the picture there. I switched from particle physics to atomic physics, but I'm still kind of interested in these sort of standard model type questions. I'm going to talk about that. Yeah, so I'll get going. So outline of what this talk is, I'm going to give you a little bit of motivation for what I'm measuring, why I think it's interesting. I'm going to give a really brief background on the measurement tool I use, which is called atom interferometry, and then I'll give you a little overview of how my experiment works. So my experiment is measuring something called the fine structure constant, also denoted by the Greek symbol alpha. So alpha is a parameter of the standard model. It quantifies the strength of electromagnetic interactions. And it's kind of this ubiquitous number. Maybe you've even already seen it in some of your classes. It's approximately 1/137, although my experiment is trying to measure it much more precisely than just this fractional representation. And it's this number that pops up everywhere in physics. And so we can measure it with many different experimental techniques and compare these measured results to see whether our underlying assumptions and theories are consistent. So if all these measurements agree, then it's like, great, our theories are working well. If we measure this number and we measure it in 2 different ways and get 2 different results, then there's something that we don't understand about what's happening. So the kind of big picture goal with my experiment is to test the standard model. So if you've heard of the standard model before, this is one of our triumphs in physics. It's a really powerful predictive model that describes all of the elementary particles and is kind of like a cookbook for how they interact with each other. And it's quote unquote the most successful theory ever, but there's pretty compelling evidence that the standard model is incomplete or maybe even completely wrong because there's some observed phenomena that it just doesn't explain, including gravity, which is a pretty big one. Things like dark matter and dark energy that we don't totally understand and are not explained in the standard model. And then even some of the things that it does explain, it doesn't quite get right. So like this matter-antimatter asymmetry, And particles like neutrinos have some unexplained properties, like we don't understand why they have mass. The standard model predicts that they shouldn't. So there's compelling evidence that there's some physics beyond the standard model, and we're hoping that experiments like these can start to push us towards that. Yeah.
Having some audio issues.
Yeah.
I'm gonna move the. Would it be possible to move?
Should I be closer to the computer?
Would you be able to stand on this side?
Yeah.
And if we can turn it this way.
Is this better?
Maybe. Joseph? How's the audio? Joseph? How's the audio?
Can you hear me? Hello. Yeah. This is better. Okay, great.
Awesome. Thanks.
So right now there are two really precise ways that we can measure alpha, the fine structure constant. One is by measurement of the electromagnetic moment. That's a different experiment, but I'll describe it briefly. And then the second is atomic recoil. That's the experiment that I'll tell you about. So briefly, the other way that you can measure alpha really precisely is through measurement of this G-2 quantity, which is also called the anomalous magnetic moment of the electron. There's this theory, QED, which is the standard model applied to electromagnetic interactions. And QED predicts the relationship between this G-2 measurable quantity and alpha, the fine structure constant. So you can measure G-2 by measuring how an electron moves in a magnetic field, and people are really good at doing this. And then all of these A numbers, A2N, A weak, AQCD, these are standard model calculations. Some are just like number crunching, Feynman diagrams. Combining these two things, you can deduce a value of alpha. The other way, which is what my experiment does, is to measure alpha through atomic recoil. So atomic recoil, if you imagine you have an atom and you send a photon at it, the atom may absorb the photon. When this happens, all of the momentum that was in that photon now gets transferred to the atom. So it experiences an atomic recoil. It just like gets a little momentum kick. This momentum kick depends on the momentum of the photon, h bar k, and the mass of the atom. So we get something that looks like h bar k squared over 2m if we write it in angular representation. So this like h over m part in the atomic recoil can plug into this definition of alpha, and that turns out to be kind of the bottleneck uncertainty when we're trying to make direct measurements of alpha. So everything that's like in this definition of alpha in the orange box, we've already measured really precisely, and the bottleneck precision is this h over m term that we can measure with recoil.
Do you have a question?
Yeah.
What is PPT?
Oh, that's a great question. So PPT is parts per trillion. So that's the precision of these measurements. So all of these quantities in orange have been measured to like better than 100 parts per trillion. That's like the, like 10th decimal point. And then the h over m, we're trying to improve on the best precision, which is 200 parts per trillion. Yeah, and yeah, jump in with questions as I'm going. Thanks for asking that question, Joseph. So to summarize, we're measuring atomic recoil really precisely at the sub-part per billion level. Doing this will allow us to determine alpha, the fine structure constant, and then we can test the standard model by comparing this measurement of alpha done with atomic recoil to measurements done with the G-2 measurement. So yeah, part per trillion measurement. So we're like deep in this expression. So right now the measured value of alpha is 1 over 137.035999, and then like those next two decimal points are what we're trying to zero in on. So this is where maybe there's some like new physics and dark matter hiding out that we want to like test deep in these decimal points. To kind of visualize that, so here's the G-2 expression, and this bar chart are these different terms, like the A standard model calculations, and the dashed lines correspond to the precision of the alpha measurements. And kind of what this graph is supposed to show you is that we're like probing this A10 term, which is a 10th order QED calculation. So this involves like 10,000 Feynman diagrams calculated together. It's a really hard calculation to do, as well as these other like really high order terms to this expression. And as we keep pushing the precision of these experiments further down, we'll start to become sensitive to even new standard model contributions to this term. So this becomes a really powerful test of the standard model that we can do with a kind of relatively small scale experiment, which is cool. These are kind of the recent measurements of the fine structure constant. The orange data points are the G-2 measurements, and the green and blue data points are the recoil-based measurements. And so the goal is to compare the recoil measurements to the G-2 measurements. And you may notice that the G-2 measurements have very good agreement between themselves, and the recoil measurements do not have good agreement between themselves. So there's kind of like first order of business is to get all of these recoil measurements to agree so that we can this disagreement is probably not due to any like new beyond standard model physics. It's probably experimental error. And so with the new experiment that I've been building over these years, we're hoping to clear up this discrepancy so we can, you know, make an interesting comparison between the recoil measurements and the G-2 measurements. So that's the end of the motivation section. Does anyone have any questions on that before I move on? Yeah.
Why is there 3 9s in a row for value of alpha?
That's just random. Maybe there's some deeper reason, but we don't know what it is. Yeah.
Can you repeat the question?
Oh, the question was why were there 3 9s in the definition of alpha? And I'll let you know if there's a 4th 9, but yeah.
Since for like, you look at the next one, the like depth gain per unit decimal.
Yeah, so the question was like what's the depth gain per decimal? Yeah. So this plot is scaled to part per trillion. So it's kind of like the size of the next correction that we could probe would be like maybe this weak correction. So we would need about a factor of 10 improvement. So like one more decimal place, and then we can see the contribution of the weak term, which is that last bar. Yeah, and so it kind of like depends on like the size of the different contributions. I don't know how big the 12th order QED term is. It's not on this plot. Yeah, so there's not like a one-to-one scaling though. Yeah. Any other questions? Yeah.
Why do they use group near 87 as one experiment? Why do they use this kind of?
Yeah, so good catch. So in our experiment, we use cesium-133, and in the other experiment, they use rubidium-87. Cesium and rubidium are both really nice atoms to use for this sort of experiment because they're alkalis. So they're in the first column of the periodic table, and that means they have one valence electron. And that's just really kind of gives you very convenient electronic level systems. You're basically just moving that one electron around, and you can ignore the rest of the electrons. And this is true for both rubidium and cesium. And when you're choosing between rubidium and cesium, there's different trade-offs. There's not like one that's definitely better than the other. And it's kind of interesting for science to make measurements with each. So that's why they use rubidium and we use cesium, but there's, they're kind of mostly equivalent. Yeah.
What about other alkali metals?
Yeah, so there are other alkalis. There's like lithium, there's potassium. The kind of short answer is that they have less convenient, like if you have to build harder lasers to access their one valence electron. And it kind of just works out that rubidium and cesium have kind of convenient energy level transitions that in terms of laser engineering. Yeah. So these are rubidium and cesium are probably the two most common alkali atoms that you'll see in AMO experiments. AMO is atomic molecular and optical physics. Yeah. Okay, so I am now going to tell you a little bit about atom interferometry, which is the tool that we are using. So properties of a wave. You've seen waves before. If you're describing a wave mathematically, it has an amplitude, that's like the height of the wave. It has a frequency, that's how fast it's going up and down. And it has a phase, which is like if you translate the wave back and forth, like where did the crests and peaks fall? And the phase is the important parameter for everything I'm going to describe. So just think about phase of a wave. Waves will interfere based on the relative phase. So if you have two waves and you overlap them, if they have constructive interference, if the waves are in phase, they'll add and you get constructive interference. You get one big wave. If they're out of phase, then they'll cancel each other out and you get destructive interference. Atoms are waves too. The wave particle duality of nature says that everything is both a wave and a particle. And particles of matter, like atoms, can act like waves, especially when they are small and cold. So there's a de Broglie wavelength that describes like what is the wavelength of matter. And if you have something that has a really small mass or a really small velocity, it's going to start looking more and more like a wave. So in our experiment, we take something small, an atom, we make it really cold, and then we use the wave properties of this atom and we create interference that we can measure. So to give you a little example, so we start with an atom, we give it some initial wave function, psi naught. If you've taken quantum mechanics, you're very familiar with this Greek letter psi. If not, just imagine that psi kind of contains like the initial conditions of this atom, like where it is, what's going on inside of it. And then it has some initial energy, E naught. When we shoot a photon at it, a photon is a particle of light, then the atom will absorb the photon, absorb momentum that the photon had, and it'll get this recoil. So now it has a little bit of extra energy from that recoil. Basically, all the energy of the photon has been transferred to the atom. And then it'll kind of, this is, we're imagining this is actually happening. It like flies up a little bit. It's under the influence of gravity. It comes back down. Now the atom wave function has evolved in time. So if you've taken quantum mechanics, you recognize this is the time evolution of the Schrodinger equation. If you haven't taken quantum mechanics, all you need to know is that our initial wave function now has this phase term on it. So when a wave function evolves under time, you get an extra complex phase that depends on the energy and the time. So if you look for some period t and your particle has some energy e, then you get this phase that goes like I times et. Okay, so we're going to do that again, but we'll do it in a superposition now. So we're sending a photon at our atom, and we're going to say there's a 50% chance that nothing happens, and a 50% chance that the atom absorbs this photon and gets the recoil. This is really like a quantum superposition. Both of these things are happening at the same time. So half of the wave function, nothing happens. It just sits there with its initial energy. The other half of the wave function now has this extra energy from the recoil, and it flies, it comes back on. And the wave function has evolved, but it's evolved differently depending on the difference in energy between the two states. I see some people are already laughing because you see the analogy I'm going to make. So Eevee is the Pokemon that can evolve into different final states. So in one half of our superposition, we got some final state that depends on just the initial energy E naught. And the other part of our wave function has some different phase from the extra energy from the recoil. And crucially, we now have a phase difference between these two states. So we have a phase difference that depends on the recoil energy, and this phase difference is going to create an interference that we can measure in the lab. So this interference signal becomes like a population difference in an ensemble of atoms that we can measure. And so this looks like some kind of interference signal like that when we're looking at many atoms. Yeah, you have a question? How do you create the superposition? That's a great question. I'll talk a little bit more about it in a future slide. I won't get that into detail, but basically you can create so when you like turn the crank on atomic physics, you get this phenomenon called Rabi oscillations, which is basically like if you're exposing an atom to some radiation, the atom is going to oscillate in population between two states. So here we're considering like one state and like a state that's like has absorbed the photon, and there will be Rabi oscillations between these two states, and that's kind of something that like pops out of the math when you're studying atomic physics. And so you can do a pulse where you're like halfway up on the Rabi oscillation. So basically, it's like you shine a laser at the atom and you tune the intensity and the frequency of the laser in such a way that creates this 50-50 superposition. Yeah, probably not a super satisfying answer, but we can talk about it more after.
Like oscillations, like they just oscillate between two states.
Yeah. That was a great question. Are there other questions about? And I guess I'll say there are a lot of different ways that you can create. Well, I won't go all the way back. There are a lot of different ways you can create this 50-50 superposition. And all of those techniques are generally called like beam splitting techniques, where you're using often light, but sometimes other things to split your beam of atoms into two. So it's kind of like if you have a laser beam, you can create like a beam splitter with like a plate of glass. And now we have like atoms and we're creating beam splitters with lasers. And there's actually like a whole class of different techniques that do this. Yeah. Any other questions about atom interferometry? Okay, great. I'll go on. Okay, so the alpha experiment. I showed you this picture. This is what the thing looks like. So it's an atomic fountain, meaning we start with a bunch of atoms at the bottom of the fountain, and then we launch them. They travel in free fall. They fly through our fountain. We do this interferometry stuff to them, and then we detect them when they fall back at the bottom of the fountain. It's a 5-meter tall fountain. You can kind of see in this picture, it like extends into a hole in the floor of our lab that we call the pit, where I've spent a lot of time doing unpleasant optical alignments. We have cesium atoms because they're alkali atoms. They have convenient electronic structure. And we have a lot of lasers. Lasers are the main way that we talk to the atoms throughout this whole process. So this vacuum chamber has a bunch of windows on it, and we shine lasers in through the windows to talk to the atoms. So I said I joined this project in 2019. In 2020, we installed their new vacuum chamber. It's like this Russian nesting doll of all these different like magnetic shielding layers that we assembled ourselves with this really like janky crane that we attached to the building on a Saturday when Anthony wasn't around to yell at us. That's my PI Holger at the bottom holding on to the chamber. We installed it into the lab, and yeah, now it's there, and we're going to kind of magic school bus journey through the atomic fountain with the atoms. So it starts, we have them pull the atoms at the bottom of the fountain, we launch them into free fall. Now they're just like traveling just under the force of gravity through the fountain. We use lasers to apply the momentum superposition. We tune the frequency and the timing of the lasers that we get these 50-50 pulses. We let the atoms propagate for some time in these different momentum states. Because of their difference in energy, they accumulate a phase difference. And then at the end, they fall back through the bottom of the fountain. This phase difference creates an interference signal that we measure by measuring the populations of atoms. Then we get the atomic recoil, and atomic recoil gives us alpha, and then we, the theorists tell us what that means about the standard model. Okay, so we'll go a little more into detail for each of these steps. So the first step, we trap and cool the atoms. So why do we need cold atoms? Cold atoms have a very well-defined velocity. And if you remember this form of the de Broglie wavelength, a well-defined velocity or a small velocity spread will create a large wavelength. And so basically, the atoms, when they're cold, they start to look less like particles and more like waves. So that's kind of the main reason why we want to have cold atoms. The way that we make the atoms cold is with lasers. So there's this phenomenon of Doppler cooling where if you shine lasers at your atom from all directions, it actually makes them colder. This is kind of blew my mind when I first found out about it. It relies on this Doppler effect. So the Doppler effect you may be familiar with. If where the frequency of a wave depends on the velocity of an observer. So if there's some wave traveling at some fixed velocity and you're moving towards the wave, to you, it will look like a wave with a shorter wavelength. If you're traveling away from it, it's like the wavelength gets stretched out. It looks like a longer wavelength. So this is also true for atoms moving around in a laser field. So we can use this in this way. So we'll tune, there's some like specific resonance frequency where the atoms will absorb photons. We will tune our frequency a little bit away from this resonance frequency in such a way that when an atom is moving towards the laser, it will be absorbing photons and kind of gets like slowed down. And if it's moving away from the laser, it looks like the laser's off resonance, nothing will happen. And you get a net effect where anytime the atom is moving in the direction of the laser beam, it gets slowed down. And the net effect is slower, colder atoms. Someone I used to work with would use an analogy of like, it's like you're being pelted with tennis balls from all directions. And then you just eventually can't even move if you're just getting tennis balls thrown at you from all sides. That's kind of what we're doing. We're like throwing photons at the atoms from all sides and slowing them down. And slowing down the atoms is equivalent to reducing their temperature. So we have 3 pairs of counterpropagating lasers from all sides. This on its own is called an optical molasses, which is also kind of a very descriptive term. So it's like you can imagine the atoms are like stuck in like a sticky molasses of the laser beams. You additionally add magnetic field gradients with two electromagnets, and this creates a trapping force. So then we end up with a cold localized cloud of atoms that we call the MOT, the magneto-optical trap. And if you're interested in atomic physics, if you start learning about more atomic physics experiments, you'll see MOTs all over the place. It's kind of like the workhorse of atomic physics. It's a really powerful and popular tool for creating a cold localized cloud of atoms ready to do experiments with. When we were first setting up our MOT, we found that the MOT is very sensitive to the alignment of the beams. And so when we were first aligning the beams, we created a lot of really horrible looking MOTs, but now we have it working very nicely. These are MOTs. They're just badly aligned MOTs. So this is just like a cloud of atoms in a really crazy looking shape. The one on the left we called, I don't know how well you can really see it in the projector, but it kind of looks like it has wings, and we called it the moth MOT. The one on the right was this like crazy ring shape that we like accidentally created. Yeah, so these are pictures of the atoms that we took with the CCD camera. this is what it actually looks like in the pit. So it's like looking down at the bottom of our vacuum chamber. So this is kind of just like looks like an experimental mess, but if you squint your eyes, you can maybe convince yourself there's some lasers coming in through the windows. They're traveling in. If you can, it's hard to see in this picture because everything is blue, but there are these like blue wires coming in from the left. Those are fiber optics. So those are like wires that are holding laser light. And then there's optics that collimate the light and send it through the viewports that you can't even see because there's so much stuff there. And there's also 2 electromagnets. So those are just wires with current running through them, and it creates our magnetic field. This is what the MOT actually looks like in the pit. It looks horrible. This is what the laser system looks like. So to kind of give you a flavor of what typical, laser stuff that we use in our lab looks like. We have all these components. So we have diode lasers, we have tapered amplifiers, which take in a little bit of light and amplify it into a lot of light. We have isolators that allow light to travel one direction, not the other. We have mirrors, we have beam splitters, we have optical fibers, we have lenses. All this stuff looks like this on optics table. We actually have like tables and tables and tables full of, of optics, but here's one little snapshot of what one of our MOT laser systems look like. Okay, so we've trapped and cooled the atoms. We launch them into freefall. They travel through the fountain. There they go. Wahoo! We use, again, lasers to put them into momentum superposition. So to do this, we have a laser that comes in the bottom of the chamber, and there's a mirror at the top that reflects it back down. And we use a process called Bragg diffraction. So this is one way that you can do this beam splitter. And this, the way that this works is we create a standing laser wave. So the laser comes in, it retro reflects back down, and these 2 beams interfere and create a standing wave. This standing wave looks like a diffraction grating to the atoms. So the atoms, when they're traveling, they diffract off of this grating that's created by the standing wave. What's happening quantum mechanically is that the atoms are absorbing and emitting photons, and this results in an atomic recoil from conservation of energy. So if you look at like a simulation, it looks like you have some atoms coming in, you apply your grating, and then you get a splitting that comes out. So this is our Bragg diffraction tool to create our momentum superposition. So now we have 2 clouds of atoms, or really we have 1 cloud of atoms split in a superposition with 2 different momentums. We let this cloud of atoms time evolve and accumulate a phase difference from this difference in energy. Really, we do this twice. So this diagram is a little bit scary, but it's not actually that scary. So on the x-axis, this is time, and on the y-axis, this is position. So this is a diagrammatic representation of what's happening to the atoms. So if you start from the left, you have this atom cloud come in. We've already launched it, so it's kind of like traveling on some like parabola of just like falling under gravity. Then this first dashed line is our first beam splitter. So now we have 2 clouds of atoms that come out of that first beam splitter. Then every dashed line after that is another beam splitter. And if you look at just the bottom 2 lines, the red line and the dark blue line, you see that they have a different average kinetic energy over the course of their trajectory. So then when they interfere at the end, they have this phase difference from that difference in kinetic energy from the recoil. They're also at a different height in the chamber. So that means that in addition to measuring the difference in energy from the recoil, we're also measuring the difference in energy of just the gravitational potential at those 2 places. Like they'll experience a different gravitational force. And in order to correct for this, we do 2 interferometers at the same time, where one of them is upside down. And then we can compare the differential output of this and the difference from things like gravity and also vibrations or laser noise that all cancels out. And then we get one differential signal that contains just the recoil. And so we actually have 4 EVs at the end that have all evolved differently. It's called a simultaneous conjugate interferometer because we're doing 2 interferometers at the same time, and their conjugate, one of them is upside down to cancel out gravity. So we time evolve our 4 EVs, we accumulate a delta phase, then eventually they fall back through the bottom of the chamber where we have a detection chamber, and that's where we measure the interference. the way that we measure the interference is with fluorescence detection. So we do this with lasers, shocker. We shine lasers at the atoms. The light is resonant, so the atoms absorb the photons, and then they'll, absorb and re-emit, and this creates fluorescence, so the cloud of atoms just glows. And we use giant lens and a photodetector to collect this absorption, and then we can measure the population of the atoms from this signal. So we get something that looks like this. So we have 4 EVs falling through our fountain, and we have a light sheet, and each cloud falls through this light sheet. And so then we see a time of flight trace. So the x-axis here is time, and the y-axis is photodiode voltage. And so we see 4 signal peaks. Ignore the big one in the middle. That's nothing. We see 4 signal peaks. And these 4 signal peaks together give us an ellipse where the gravity and other things, all these common mode effects, trace us around the ellipse. And the differential phase of the ellipse is encoded in the shape of the ellipse. So we do statistics to extract the ellipse parameters, in particular the shape of the ellipse is what we're most interested in, and then that gives us the differential phase that we're trying to measure. So the status of this, I joined in 2019. We spent 5 years building this thing. We installed our vacuum chamber, we trapped atoms, we interfered the atoms, we turned every knob on the thing to try and optimize the signal to make it better. It took a long time to do this. Now this past year, we've been taking data, studying the systematics, and hopefully eventually I'll graduate. So that's the goal. This is the group that I'm a part of, Holger Mueller's group. He has a lot of different experiments. So alpha is mine. I circled my face and the other grad student that I work with, Jack Roth. Nadia, who's here, has also been working with us. She's not in this picture, sad, but she's been working with us for over a year now, doing really great work. Holger has a lot of cool experiments. Some of them are atom interferometry. Some of them are more on like the biophysics side of things, if you're interested in that. So we have a group website that you can check out. I also put my email address up here. So if you're interested in learning more, send me an email, come by for a lab tour. We love giving lab tours. Yeah, thanks so much for listening, and I'm happy to take any questions.
Any questions first?
Question about how you create this momentum superposition again?
Yeah, how we create the momentum superposition. Yeah.
I guess just as a clarification. So you're saying that like you shoot at like an ensemble of atoms, and then the retroactive beam creates like this like infinity.
Yeah.
And
Yeah.
so it literally just like deflects like 2 different directions.
Yeah, so we do this with an ensemble of atoms, but this is something that really happens on the individual atom level. So you can just imagine one atom, and it has, it kind of looks like a wave because it's really cold. And if you imagine like a wave going through a grating, you can create like diffraction through a grating. So this is like, like prisms will do this, and there's I don't know, I shouldn't get too deep into this rabbit hole because it'll just be too confusing. But basically, yeah, the laser comes in, we create a standing wave. This looks like a diffraction grating to the atom, and the wave function diffracts through the grating. But what's actually happening is the atom is like absorbing and emitting photons from these counterpropagating beams, and that gives atomic recoil to creates one state that gets this atomic recoil and one state that doesn't get this atomic recoil. So it's kind of like one state, it's as if it didn't interact with the light at all, and one state absorbed and emitted photons and got like a momentum kick from doing that.
Sorry, out of
Yeah.
curiosity, what's that characteristic that determines whether it's
So there are a couple characteristics. What the 2 parameters that really matter are the intensity and the frequency of the laser beam. So these are 2 parameters that we have to tune really precisely in order to get this diffraction. And then you can tune those parameters also to control the like ratio of diffraction. So you can tune them so that like you have 100% transfer into the diffracted state, or you have 0% transfer, or 50-50, which is what we're trying to achieve, or like 30-70 if for some reason you wanted that, so you can like tune these parameters to like transfer more or less atoms into your desired state. Yeah.
Is it a smooth distribution of the number of photons each atom absorbs, or is it like peaks at different places?
So it's
Can you repeat the question?
oh yeah. So the question was, is it a smooth distribution, the number of photons that the atom absorbs? So it's like a quantized thing. So the atom can only absorb like quantized number of photons, and this is kind of determined by the frequency of the laser. There's only like one condition that is allowed. So here, actually, I think I have a backup slide. Yes. Okay. So if this is helpful, then and if it's not helpful, then it's fine. But so basically, we tune the frequency of the light so that we're exactly matched with some higher order momentum state. And so there will be one higher order momentum state that's resonant, and it will correspond to a specific number of absorbed and emitted photons. And so it could be like it has to actually be a multiple of 2. And so it could be like 2 photons or 4 photons or 6 photons, but it's only ever going to be one of those. We get like a little bit of like kind of a junk ports of atoms that will maybe hit the wrong order. So if we're aiming for like to transfer 6 photons, and like a small fraction will transfer 3, or we'll transfer 4 photons instead. So, but it's determined. The short answer, the TLDR, is that it's determined by the frequency of the lasers.
So how many of the atoms absorb 2, absorb 4, 6?
So this is something that we kind of simulate, and it's like 99% of the atoms will absorb the desired 6 photons, and maybe like 1% or less than 1% will absorb 4 by mistake. I keep saying 3 because we do third order, but that corresponds to 6 photons, but it doesn't matter. It's a pretty small fraction because it is an off resonance. It's like not a resonant transition. Where resonance means that like the energy of the photons matches the difference between the starting state and the final state. Yeah.
Just how long are the atoms flight when you like shoot them up and they go back down?
That's a great question. It's about a second. It's a very like physical time scale. It's like, this 2-meter chamber, and we launch, and it's kind of like if you just like threw a tennis ball and then like it flew up and then landed back in your hand. It like takes about a second. Yeah.
So like what led you to, or what led people to decide on 5 meters?
So there are people that are built. So the question was why is the tower 5 meters tall? Why not shorter or larger? There was this measurement done in my group in 2018, so kind of right before I joined, that was done with a 2-meter fountain. And then Holger was like, bigger, let's build a bigger one, which is kind of, I would say, the general sentiment. There's a lot of people that are trying to build bigger and bigger fountains. So there's actually 2 fountains at Stanford that are 10 meters tall. And there's a fountain being built, kind of in the process of being built at Fermilab in Chicago, that's going to be 100 meters tall. And people are like, we're going to build 1,000-meter fountains in space to measure gravitational waves, and like all of these crazy proposals. So people are trying to build like bigger and bigger fountains to be sensitive to smaller and smaller perturbations. What was the question? Why is a bigger fountain preferable? Yeah, that's a great question. So why is a bigger fountain preferable? Oh, back. Okay, so basically we have this phase difference that is proportional to whatever energy difference you're trying to measure times the propagation time. And for longer fountains, you can have a longer propagation time. If you're trying to, measure smaller and smaller contributions, you can either like make this energy difference bigger, or you can make the time bigger, and or you can make many more measurements. But you're kind of limited by like the lifespan of a PhD in that sense.
Shouldn't the phase return to 2 pi that's 0?
Yeah, that's a great question. So the question was, does the phase just return to 2 pi and become 0? So it kind of has to do with like the fact that so the phase does come back to 2 pi it like wraps around, but you're measuring kind of like small phase differences on top of this like large total phase. So the larger total phase that you're accumulating, the like better fractional precision you have for like the amount that you can resolve the shape of this ellipse. Is that a satisfying answer? Okay.
In the fluorescence measurements, you asked us to describe the central spike. Is that just the laser, or is that some other like fluorescence?
So in this trace right here, so that's a background peak from a part of the experiment I didn't talk about, which is in this diagram. There's this red stripe in the middle. That's something called block oscillations, which actually is what Nadia is working on. The block oscillations accelerate these two conjugate interferometers away from each other and give us an overall sensitivity boost, and that process has a kind of bad efficiency, and so the atoms that don't successfully get accelerated away are left behind in the middle.
I remember that either in the alpha by this recoil requires 4 factors. So you have 4 factors and of that alpha. And are the measurements for other parts of the other parts are independent?
Yes, that's a great question. So, yeah, sorry, what were you saying?
Just you need to measure 4 parts.
Yeah.
Those are independent measurements?
Yeah, so the question was, we have to measure all 4 of these quantities. Are they independent measurements? And the answer is yes. So the first quantity is this Rydberg constant, so that's measured through hydrogen spectroscopy. These next 2 quantities are mass measurements made, they're relative mass measurements, so it's the mass relative to the atomic mass unit U. So these are made with penning traps, like you measure precession frequencies of atoms and you compare them to like a reference atom inside your penning trap. So these measurements are done in the same way, but they're independent measurements. One is the mass of the electron in atomic mass units, and the other is the mass of, in our case, the cesium atom in atomic mass units. What's kind of interesting is that some of these, so like the Rydberg constant in particular, does have like some standard model calculations baked into how you extract the Rydberg constant from hydrogen spectroscopy, but it's a much smaller contribution to this measurement of alpha. So that's why you don't have like a circular logic when you're comparing these quantities. But there is some standard model stuff like hidden in there.
So what's the expectation for your experiment?
What was the
expected precision?
Yeah, the question is, what is the expected precision of this experiment? When I joined this experiment, that green LKB 2020 measurement didn't exist yet. So we just had these 3 on top. So our goal was, okay, let's make a measurement maybe with factor of 10 improved precision and see if we can resolve this discrepancy between G-2 and atomic recoil better. But the goalpost shifted a little bit when this green LKB 2020 measurement appeared. And so right now we're focusing more on like a more rigorous systematic study to like be more confident in some of the challenging systematics that we have to account for, to try and clear up this discrepancy between the 2018 Berkeley measurement and the 2020 LKB measurement. So we'll make a measurement of a similar precision to 2018, so 200 parts per trillion, and try to add more confidence to the systematics procedure.
Yeah, so one more chat question. There's implications that basically the alpha fine structure constant could have been different at different points in the evolution of the universe. Does your experiment offer any like implications to that structure constant having changed, or anything about the models about actual cosmological evolution?
Probably not, because we only have access to the current value of alpha right now. And there are also some interesting theories where it's like, oh, the value of alpha is like slightly fluctuating in time due to like an oscillating dark matter background field. We're also not really sensitive to that sort of thing because we have to average over such long times to make this measurement. So we're really most sensitive to like these sorts of like comparison tests where you're comparing different methods of measuring the fine structure constant and testing the theories that generate them. It'd be cool if we could like do some sort of like cosmological like historical alpha measurements, but like you know, you can't really shed too much light on that with this, unfortunately, just because we're anchored in time right now. Yeah.
All right, let's thank our speaker one more time.
I'll stick around too if people have more questions.
Thank you all for coming. We will be back next week with a talk on gamma ray detection using a massive telescope. Come back next week to hear more about it. And also, if you haven't signed in, please sign in on your way out. Thank you very much.